Welcome to reinforcement learning, and we're going to learn how to solve for state value functions in a system of linear equations. So the idea of this session is to get some intuition about the technicalities of the value iteration algorithm, and this is going to be useful because lots of reinforcement learning algorithms are actually based on different versions of the value iteration algorithm. And sometimes we then see which properties carry over and which properties get lost. The idea of value iteration is to optimize a value function and then induce a policy. Now we're gonna see properties of the policy evaluation and also of the value iteration. So we can summarize the value iteration algorithm for a Markov decision process by taking a look at this algorithm. So we initialize at any value, and basically, so that's the last steps value here, and where we take the just the rewards. So like in the example we had last time, and now we do then the update of the value function estimate by just taking the maximum of the rewards that are a function of the state action pair and the discounted expectation of the future rewards. Now here the optimal policy is pi star, and it's gonna be just the argmax of the last step basically. And in the steps before the last step, it's gonna be the argmax of the reward function here plus the discounted expected cumulative rewards. Now T here is the number of time steps still to go until the end of the process, and the pi is gonna be non-stationary. That means it's time dependent, so we will have in the last rounds a different policy possibly than in the rounds before, so endgame effects. Now let's take a look at a simple example where we want to take this into matrix notation. And for this we write up a column vector for rewards for each action A. And here you see RA1, that's the reward vector for actions for the action A1. So here for each of the states S1 and S2, we have two numbers, 0 and 10. And for action 2, we also have a reward vector with a -5 and +5. Now also we have a S times S transition matrix for each of the actions. So for action 1, this is the green one here, and for action 2 it's gonna be the blue one. Then we also have a vector, a column vector S times 1 for the state values. Now to calculate those state values, we want to take the max of this reward vector plus the discounted expected future rewards. And so this is going to be this maximum of the action 1 rewards that we get in right away in the state, plus the discount factor 0.9 times the transition matrix for action A times this value function of the future. So here we have then also for the second action the same thing, and we can choose then the maximum based on each element. Now with this we can rewrite the value iteration algorithm just in matrix notation, which makes things a little bit easier. And so we can consider the infinite horizon problem. So when h, the horizon, goes to infinity, we can actually take a look at the value state value vectors, and these vectors for a given policy pi are gonna be the same as the value for the policy pi at infinity, because h is going to infinity, and just one step before infinity is gonna be very similar also to the one the value at infinity. So what we do then is to replace this link between the two periods by just this stationary value function. So v pi infinity is going to appear on either side of this equation. Here for the policy evaluation, yeah, and for the Bellman equation, the same thing. So here we have v star infinity on the left-hand side and also on the right-hand side. And the difference between the policy evaluation and the Bellman equation is just this maximum that is not appearing here in the policy evaluation. So to actually do the policy evaluation, we can view this, if you write it up in matrix notation, as a system of linear equations. So here is an example for possibly non-optimal policy. So pi here has the policy that whenever we are in state S1, we take the action A1. And whenever we are in S2, we take the action A2. So we can go back to the definitions. So if we are in S1, well, then the reward will be 0 here. And the transition function has the row for S1, 0.3 and 0.7. So we put that into this transition matrix and the reward vector for this policy. And then we go back and take a look at what happens in S2. So here we have the transition probabilities of 0.2 and 0.8. And the reward is going to be for S2 5 if we take action 2. And we do that according to this policy. So we write this down in this transition matrix and the reward vector as well. Now, if we have this, we can actually write this equation as v equal r plus gamma times tv. Yeah? And this is a system of linear equations that is possibly nonlinear. So we could perhaps improve. And if you closely look at those values, you might see that there is some room for improvement. And this can be solved by a Gaussian elimination procedure or computing the inverse, or iterative methods. And well, value iteration is one of them. And it's actually also a very popular one. And we're going to see that later on. It turns out to be the only method that can be used in some applications. So that's why people use the iterative, the value iteration, which is also known as Richardson iteration. Now, how does it work? One property of value iteration is that with whatever estimate of the value function we start, we're going to shrink the distance with the discount factor. Now, to understand the intuition behind this, consider H, which is a policy evaluation operator applied to the value function. And if we have two estimates, v tilde and v, of this value function, then we can calculate the distance between the two. So this is the maximum distance here. And if we apply the policy evaluation operator to each of these estimates, then this distance will be smaller than the one without the evaluation operator. So we shrink this distance, and this is actually something that is very useful. So this H operator is what is it? It's defined as the just the vector of rewards plus the discounted expected future reward. So we have here this operator as a contraction mapping. What does it mean? That means we shrink the distance. And we shrink the distance between the two estimates that are evaluated here in such a way that this is smaller or equal to the discount factor times the difference between the estimates themselves. Now, the proof for this is that we just take here the left-hand side and plug in the definition. If we do that, we can cancel the reward vectors here. So we get gamma times the transition matrix times the difference between the two estimates and the max norm of it. If we use this rule here, then we can see that this is going to be smaller or equal to gamma times this max norm of the transition matrix, which is, by the way, 1 because it's a probability distribution, times this difference. Yeah? And so we end up with gamma times this distance between the two estimates. And so gamma is going to be decisive for shrinking this distance. The discount factor, if it's smaller, then we will shrink more. Now, do we get to the optimal value actually? Well, actually, wherever we start with value iteration, we do contract to the optimal value, and that's great. So the intuition is here. We got a guess, 0, and a guess v for the value function. So you can think about the future value function that we guess here to be 0 in the initial part, and here it has some guess v. So if we have these two guesses, then we can apply this operator, the policy evaluation operator, and this gonna shrink the distance between the two. Then we apply it again and again and again, and we end up in the true value of the value function for that state. Now, this is theorem number 2 that tells something about convergence. So it says that the policy evaluation will converge to the true value of that policy for any initial estimate. Now, so if we do infinitively many iterations, then this is going to be the true one. Now the proof is that by definition, if we do infinitively many operations of this h with the 0, so that's the last step, then we are at the true value of the policy. But the policy evaluation also computes for the policy evaluator infinitively many times applied to this estimate v for any initial estimate v. So what we do is we take the lemma number 1, so the shrinking the distance, the contraction mapping, and here we can now just take a look at what happens if we apply this many times. Then we have this gamma raised to the power of n, and so if n is going to infinity, this distance is going to be shrinking to 0, and this h of infinity applied at some estimate is going to be the true one. So that's the convergence. Now, if we stop early, how far are we actually from the optimal value? Because in practice, we cannot do infinitively many iterations. So we need to know whether the theoretical guarantees what our error will look like if we stop early. Now, suppose that we stop after n iterations, and we have this maximum distance of this policy evaluation between 2 steps of an iteration, at an estimate, and that's going to be epsilon. How far is now this estimate away from the true value of the policy? To get an intuition of this, let's take a look at this picture. So, well, if we do that in 1 iteration, we have this epsilon. If we do it in 2 iterations, we have epsilon times gamma. And if you do it again, we have this epsilon times gamma squared, and so on. It's a geometric series, so we end up in the optimal value, and how far we are away is actually determined by this discount factor. Now let's take a look at theorem number 3, where we can say something more about this. So here we have this distance between the 2 iterations of the policy evaluation operator, and this is going to be less or equal to epsilon. If this is true, then the distance to the true value at n iterations compared to the policy evaluation at that iteration level with any estimate is gonna be smaller or equal to epsilon over 1 minus gamma. And the proof is that we can just take this left-hand side here, and well, we know that this true value is going to be the policy evaluation operator infinitively many times applied at any estimate v. And so we have here the distance between that and the one where we stop at iteration n. And now we can see that, well, if we have infinitively many iterations, that's going to be a sum that goes to infinity, and that sum involves the discount factor. And so if we use this further property here, we can see that it's a geometric sum of the discount factor, and so we end up with epsilon over 1 minus gamma by lemma 1. So here we see that actually we have, if the discount factor is close to 1, then we will multiply the epsilon, the error, with a very large number. But if it's close to 0, then we will divide epsilon by something close to 1. Now, how to find the best policy? So this was only policy evaluation, and now we want to also find the best policy. Now, V star is the best policy, and so the difference is this max operator. The problem is that this max operator renders the whole problem nonlinear. Now we have a nonlinear system of equations, and we need to solve that, and that's going to be require a little bit of more thought again. So we can write up this as this matrix in this matrix form like before, and now even with the max we can get the contraction mapping, so that's the good news. So we have here now the new definition of the policy evaluation operator at the optimum, so we have a max here. And now we can write up lemma 4. So H star is going to be a contraction mapping. So we write up the maximum distance between the two estimates, and that's going to be smaller or equal than gamma of the maximum distance of the two estimates as well. Now here we can just assume without loss of generality that the policy operator at the optimum with V tilde is larger than the one without the tilde, and the policy that we extract in the current state is just the A star S. Yeah? So with this, we can then rewrite this difference between the two by plugging in the definition of it, and then we can cancel this reward vectors and factor out the gamma times the transition probabilities. And then we can, instead of these value functions, we can use the upper bound of the max norm here. And if we do that, we can then also use the fact that this sum of the transition matrix is going to be 1. And so we can write gamma times the maximum distance between the two estimates of the value function. So we have again this contraction mapping property. Now theorem number 5 is going to say that also with the maximum, so also with the optimal value, we can converge to this V star. So with infinitively many iterations we get to the best value, and the proof is pretty similar as before. So here we just do the same thing as before. We see that the lemma 4 applies, and here we have gamma to the power of n, and if we wind up n infinitively large, then this distance will gonna be 0, and we get to the optimal value as before. Now we can rewrite this value iteration algorithm a little bit different. So if we stop early then well, we can stop when this difference is smaller or equal to epsilon. So this is just the difference that we include this here, that we stop before infinity. Now, what is the induced policy and how far is it away from the maximum of the value function? So we have seen before that since this maximum difference is smaller or equal to epsilon, that this difference to the true one, so this is between two iteration steps, and here the difference between the true one and the value estimated at iteration n is smaller or equal than epsilon over 1 minus gamma. But how good is the policy pi n extracted based on this Vn? So if we take that policy out of this, so by the argmax, then how far is the value of this policy away from the true optimal policy? Now, theorem number 6 has something to say about this, and it says that it's just 2 times epsilon over 1 minus gamma. And the proof is that if we use this definition, we can actually expand this by adding and subtracting this Vn, and then we can rewrite this with this rule that we have here, and then also apply this policy evaluation operator. And basically it's that we do 2 times the same thing. So we have here this geometric sum again, and we have epsilon over the 1 minus gamma plus epsilon 1 minus gamma, and we see that 2 times epsilon over 1 minus gamma is then the difference between the two, the value of the policy at iteration n and the true value of the state, the true best value of the state. Now, policy value iteration is a simple dynamic programming algorithm. We have seen the properties. It does actually have some good properties. And the complexity of it is the number of iterations times the number of actions times the number of states squared. So this is because of the transition matrix. Now here are some references for further reading, and let's sum up the takeaways. So if we repeatedly apply the Bellman optimality, then we get to the optimal value V star. And approximate solutions help us in infinite horizon settings, so we can stop early. And we also can say something about how far we are away from the optimal one. So the discount factor is decisive here. And the policy error actually does decrease in each iteration. So that's the summary here. Thanks for watching.